All right, so I did get a few questions today, and so we're talking about them more globally. One is graphical analysis, the other is activation energy from Arrhenius Plot. They both kind of seem to be following the same issues. So there is a shift between Chem 1 and Chem 2, and the shift is the nature of the questions being asked. So Chem 1 is what we consider a very low-level concept course because you're dealing with things that are basically, here's a concept, repeat the concept. So repeat the definitions of what isotopes are, repeat the definition of what a cation or anion is. And Chem 2 is different because it's actually a quantitative chemistry, and this is going to introduce two new elements. One is a lot more math, the other is analysis. And so students are much more used to kind of a follow, kind of like a paint by numbers problem. Here's what you're given, do the thing, and then do the next thing. And the thing with chemistry 2 is that it is not, there are no procedures, there are concepts that you're being assessed on. So graphical analysis is where this really begins to first show up as students are used to seeing things like, here's a graph, tell me information off the graph. And the thing is that you can't do that anymore. You're too high a level for the questions to be phrased like that. So when we talk about graphical analysis, we have to make an assumption. And the assumption is the model. So we have to assume that our material, our reaction, follows a certain type of behavior. In this case, it's parallel kinetics and it's three forms: zero order, first order, and second order. So there are three hypotheses here. The reaction is a zero order, a first order, a second order, and these are mutually exclusive statements. A reaction cannot be both zero and first order with regards to a certain reactant. It cannot be both first and second or zero and second and so forth. Now, if we assume a first order reaction, it will look like this. So it will be linear, of concentration versus time will be linear. For first order, natural log of concentration will be linear. And for second order, 1 over concentration will be linear. So this is not true. So for a second order reaction, only this statement is true. If we plot concentration versus time, it won't be a straight line. For a first order reaction, if we plot 1 over concentration versus time, we will not get a straight line. So these three initially serve as just a testable hypothesis. So what we have to do is we have to look at all three cases. A versus time, ln of A versus time, and 1 over A versus time. Where t here is time, little t is always time. So this isn't, we don't know a priori. You just can't look at the data and go, oh, it's zero, first, second order. That's why we need the models. And we're also kind of only limiting ourselves to these very simple models. You can have Michaelis-Menten, Ellery-Dale, Illingworth-Hinchwood. There are lots of models. But this is a testable hypothesis. If it is zero order, concentration versus time will be linear. But if concentration versus time isn't linear, we can take the natural log of concentration versus time and see if that's linear. So when we take all the numbers we have for concentration versus time, take the natural log of it and plot that against time. And that's what you do for the Excel homework sheets, is that you create all three graphs. So let's say you plot the data and you get this. And we stick straight lines through all three, but clearly there's only one on here that is actually a straight line, and that's the 1 over concentration versus time. This means that it is a second order reaction, or it behaves like a second order reaction. So now these two graphs are meaningless. And they're meaningless because this is clearly not a zero or first order reaction, because those aren't linear. This is also a mutually exclusive statement. If it's linear for second order, it can't be a zero or first order reaction. Only second order reactions will give this type of behavior. So once we have this information, we can now forget these other two graphs. We don't care because it's not zero or first order. Unless your reaction is zero first order, you can't get anything off of those graphs. You will get a number, you can put the numbers in, but they don't mean anything. There's no physical meaning. Which brings us to the second part of modeling. Modeling actually says that there is a reason why it is linear. And this is not just fitting it to a straight line to fit it to a straight line. We know that in this equation, 1 over a, so we're going to get some numbers, y equals mx plus b. We know that the y is 1 over concentration and the x is time. So the model not only tells us that it should be linear if it's a second order reaction, it also tells us what the terms in the linear fit mean. So for this, the y-intercept will be 1 over the starting concentration, and the slope will be the rate constant k. Now, that's not implied, it's proven. So when you solve the second order kinetics, so if your reaction looks like r equals minus k a squared, if you do the calculus and solve it, you will get this equation. So there is a proof that this is true. So this is how you approach the kinetic models. And if you look on the course website for the discussion board for last week, where you had graphical analysis, it gave you all 3 plots, and it said, okay, which order is it? Well, that's what you do, is you look at the r-squared values and you say, okay, which one does it fit the best? It fits the second order the best. Now that you know that it's second order, you can disregard the 0 and first order graphs because they're meaningless. This isn't a 0 first order reaction. It's clearly a second order reaction. From there, you can extract out the K, you can extract out the starting concentration, and it asks you, like, what's the limitation of graphical analysis? Well, the big one here is that we have to make an assumption. We have to assume a model for our data. And the problem is that you may be right for the wrong reasons. A big example of this I like to give is my K-list mint kinetics. My K-list mint kinetics can look both 0 and first order, depending on what range of concentrations you looked at. So you actually need to study a wide range of concentrations to really find a model that's guaranteed to fit it over everything. Because if you take any curve, let me erase this. So this is what my K-list mint kinetics looks like. Rate versus concentration. If we're only looking at this region here, the rate's going to look constant, which implies 0 order. If we look down here, the rate's going to look linear with regard to concentration, so it's going to look first order. So again, we had to assume a model. Our model may fit the data, but it may only fit the data because we're in a tiny range of concentrations where we would expect to get like 0 or first or second order behavior. If we looked at this region here, we would definitely not see 0 or first order. It would sit between the two, and graphical analysis would really struggle because none of your graphs would actually fit. So this is a limitation. It assumes a model, and inherent to that assumption is that this reaction is going to behave the same over all concentration ranges, low concentrations, moderate, or high. That may not be true. You may have just happened to pick a sweet spot of the reaction where it looks 0 order or it looks first order. Now, for any power law reaction, this is our generic expression. And there's 2 terms about the rate law we'd be interested in. The first is the orders, so alpha and beta here. And the second is the rate constant K. This is going to come from method of initial rates or graphical. This kind of comes from method of initial rates, but the K itself is not that useful. So, and the reason I say it's not that useful, there's actually a term within the K that's more useful. So in this course, we talk about K when we refer to transition state theory. So TST. So for transition state theory, K follows this relationship. A, I know there's an A here for concentration, but there's no brackets here. The A here is just a pre-exponential. E to the minus EA over RT. And there is a theoretical justification for this. This doesn't come out of nowhere, but you'd have to take a higher course to figure out where this comes from. But there are 2 very important terms in this relationship. EA and A. R here is the ideal gas constant, 0.008314. If you use anything other than that, it's not going to work. And here is your temperature. So EA here is reaction specific. And A here is reaction plus reactor. So the pre-exponential factor is useful if we want to do kinetic modeling, meaning that we have a reactor, we want a reaction, and we want to know what concentration versus time looks like. But because it has reactor considerations in it, it's not globally useful. Big example of this is catalyst. You may have a great catalyst, but if you don't do a really good job of making it accessible to the reagents, you're going to have a very small pre-exponential factor A because your reactor just isn't well designed. So A is something we can control more through mechanical processes, but EA here is reaction specific. And when I say reaction specific, I mean reaction mechanism specific. And EA here is going to be true regardless of what reactor we stick it in. And EA is going to show up a lot when we start looking at, well, if you go into higher courses, you start looking at catalyzed reactions. So if a catalyst speeds up reaction, generally speaking, it speeds up reaction. Not always, but generally it speeds up the reaction. And it does it by changing the mechanism. So why does changing the mechanism matter so much? Each mechanism has its own unique rate limiting step, or RLS. The rate limiting step has the highest activation energy, EA. So let's say you want to figure out if something is a catalyst. Well, catalysts aren't necessarily well dispersed. So if you look at something like platinum, it's really hard to get platinum really well dispersed. So you may add platinum to a reaction and it slows down. But it may have slowed down simply because you've gone to a different mechanism, and even though it's catalyzing it, the platinum's not being really well utilized. So we would actually measure the reaction to find this EA. And if the EA is lower, the reaction actually takes less energy to run, so it ends up being a faster reaction, more efficient reaction. So how do we extract out EA? Well, this is where your Arrhenius plots are going to show up. Now, it is unsettling. We talk about Arrhenius plots in Chem 2. They're actually not the way you would do this in practice. What you'd really want to use is what's called an airing plot. But the theory to justify an airing plot's way above where we are right now. So we're going to say an Arrhenius plot. In truth, you would use an airing plot. So we've got this form K equals A e to the minus EA over RT. And what we want to do is we want to linearize it. We'll do this with the natural log. So if we take the natural log of both sides, break it up. We get this relationship. ln of K equals ln of A minus EA over RT. Now again, A here is reaction plus reactor specific, but we can't change A. Okay, not entirely true. For all intents and purposes, we can't change A. If it's an issue of dispersion, yes. In principle, we can make A bigger by dispersing a catalyst. But let's just say we have our reactor built with the stuff in it. A is now fixed. EA is also fixed. You can't change the activation barrier of a reaction without changing the mechanism. And R here, I mean, that's a constant, 0.008314. So there's only one independent variable in this equation, and that's 1 over temperature. So this is our dependent variable. This is our independent variable. So the way we extract out the activation barrier EA and the pre-exponential factor A is just a vary temperature. So we take the same reaction, we run it under the same conditions, ideally just because it makes the analysis easier, and we find K using method of initial rates or graphical analysis, and we do it at a bunch of temperatures, and what we'll get is an Arrhenius plot. So your Arrhenius plot of ln of K versus 1 over temperature will look like this. And if we put this to the equation, y equals mx plus b, from theory, y is ln of K, x is 1 over temperature. The slope here is minus EA over R, and the y-intercept is the natural log of the pre-exponential. So not only does theory predict that we should get a straight line from this plot, and generally speaking we do get a straight line from this plot, it also predicts that the y-intercept corresponds to the natural log of that pre-exponential, and that the slope equals the negative of the activation barrier over R. Now, in terms of reasonable answers, for A, there are no reasonable answers. And the reason that A doesn't have a reasonable answer is twofold. One, A depends on reactor conditions. So depending on your reactor is going to really set the values for the A. The second, and this is just more of a practical point, A also has the units on K. So if you look at this, the exponential doesn't have any units. So any E raised to any number doesn't have units, but K here is going to have some units. So it may be 1 over time, 1 over molarity times time, molarity over time. But even if it's just time, if we convert from hours, minutes, seconds, days, weeks, decades, all that, that's going to radically change the values of A just because we did a unit conversion. So A can be all over the place. Now for the homework, practically, it's in such a way you don't need to use scientific notation. But generally speaking, A can be like 10 to the negative 6, can be 10 to the 6, depending on what you're setting your units on K are. EA, though, has a very specific range. So for EA, the activation barrier, we expect it to sit in a range from 25 to 150 kilojoules per mole Kelvin. Now, there are definitely reactions that lie above this and below this, but for most of life, reactions live between 25 and 150 kilojoules per mole Kelvin. This is just pure practicality. Now again, I say this is a guideline. There are definitely reactions that have like almost zero activation barriers. So if you mix like 2 aqueous salts together to get a precipitate, so you mix silver nitrate with sodium chloride and make silver chloride, that thing's got like 0 activation barrier. Something like the combustion of nitrogen and oxygen in air to make nitrous oxide, that's got like 300, 450 kilojoules per mole. There are definitely reactions that sit out this range, but for any reactions that we can control with these types of kinetic models, that we can actually run in the lab and control and measure, 25 to 150. Now, you've definitely got homeworks that run the gamuts of super hard to super easy. So for the homeworks, so for the graphical analysis, there's one set of homeworks where it literally just gives you the one graph. It doesn't make you choose among the 3, and that's to make sure that you understand which graph corresponds to which kinetic model, and then how to extract out the chemical information from those kinetic models. So one will be concentration versus time. Oh, that's a 0 order. You'll know how to take that 0 order graph and extract out the K in the starting concentration. It also does 0 and first. Then there's one where it gives you 3 graphs and it says, okay, which one is it? Now start filling it in. Added difficulties, now you have to figure out which one it fits. And now that you know which one fits, you know which one to use. The hardest difficulty uses those Excel sheets. You actually have to take the concentration versus time data, which is what you would measure in a lab, which you're actually kind of measuring with that iodine clock lab you did last week. And from there, based on concentration versus time, convert to natural log of concentration versus time, convert to 1 over concentration versus time, figure out which plots are linear, and then it's back to the homework again. So it's kind of like this nesting doll. The center is that one homework where it just gives you the one graph and you extract out the connected information. The one outside that is the one that gives you 3 graphs, and once you figure out which graph to use, now you're back into the center one where you use that one graph to figure out all the information. The Excel homework is like the 3rd layer. You have to produce the graphs, and then once you have those graphs, it'll be like that homework where you're given the 3 graphs, you have to figure out which one works. Once you know that, it's back to that first homework where you had the one graph and you extract out the information. For the Arrhenius plots, there's only one way to do it, and you've only got 2 homeworks on that. You've got one where it gives you the Arrhenius plots, and then the Excel sheet where you had to build the Arrhenius plots. The reason for making you do these Excel sheets is to get you out of the mindset that that's what you measure in the lab. We do not measure ln of K in the lab. We never measure K directly. It's always extracted out of kinetic models. So we get K first, and then we convert to ln of K. In the lab, we don't measure natural log of concentration or 1 over concentration. That would just be plain stupid. Like, you don't care. So in the lab, we don't plot natural log of concentration versus time or the 1 over concentration versus time. That's just not measured. What we measure is concentration versus time, and then we convert those based on that data to these graphs to see which one fits the kinetic data. And hopefully you'll see this when you do the labs. Like, this is what you measure as concentration versus time, but that's only going to be linear if it's a 0 order reaction. If you're lucky, that's what it ends up being. But you need to look at these other 2 plots, ln of A versus time and 1 over A versus time, and from there extract out whether it's a 0 first or 2nd order reaction. And that seemed to be the only questions I had. But yeah, you're starting to see the shift now to Chem 2. Test 1 was very much Chem 1. Take a formula, solve for a variable. Here you're having to do analysis. You're having to critique the data to figure out what's going on. All right, so that's it for my emailed questions. Are there any questions out there from anyone watching? Graphical Analysis, some examples, including the discussion board, include the equation of form y equals mx plus b, but we look at the equation to find the values of k. Would we look at the equation to find the value of k, or do we have to directly solve for k using points and find the slope? So that's why the joy of Excel. So in all three plots, and there is a theoretical justification for this, concentration A versus time, ln of A versus time, 1 over A versus time. The slope is always k. I'm going to put the squiggle here for it goes as. The reason is that for 1 over concentration versus time, that's the only time k is actually equal to the slope. They're all negative k, or they're all the opposite of the slope for first 0 and first order. The big thing to keep in mind, though, is that this statement is only true if it's a 0 order. This statement is only true if it's first order. This statement is only true if it's second order. All three plots are going to have the numbers in there. They're already going to have the slope in that y equals mx plus b. But the slope doesn't have any physical meaning unless that's the plot that corresponds to that reaction kinetics. So if you have, let's say your reaction's first order, the slope here is meaningless. It doesn't really, it's just a line. And the same thing's true here, it's just a line. So only if you have a first order reaction can you connect the slope to the k. But when you have a graph that does correspond to that particular reaction order, that's when you can definitively say, yes, the slope is equal to the rate constant k. So for 0 and first, if you look at the kinetic model, that's just what ends up falling out. And if you look at the second, when you linearize, you end up getting that. So that's where the -1 is coming. Now, there is a very strong theoretical justification for why k has to be greater than 0. And the reason is that k is a probability. So you can't have negative probability. So in all cases, regardless of what you do, you have to end up with a positive k. And that's a way of disproving like terrible kinetic models. I mean, most people don't ever encounter those. But you should always have a positive rate constant k because it's the probability. And specifically, it's the probability of reaction between reactants. So generally, the easiest answer is to say that we know that k is a probability. So your k always has to be positive. But in terms of the kinetic model, 0 first, like you can prove that the slope is the negative of the rate constant k. And for the second order, the slope is the rate constant k. But it's kind of hard to explain, like, unless you can really see how the model connects to the data, it's kind of hard to see that. You're welcome. currently working on test 2 orders from graphs of concentration and I'm able to get very close to everything except the initial concentration of A. Linear equation plugging in 0 to find that value. Is there something I'm doing wrong? So let me bring up that homework. My initial guess is that you aren't necessarily using, so if you're at your equation y equals mx plus b and you want to find the initial concentration, you can say that, well, the concentration is when time equals 0, so we can just look at the y-intercept here, b. So the question is, what's y? So for a 0, first, and second, for a 0 order, y is the concentration of A, so your y-intercept is the starting concentration. For a first order, it's the natural log of A. So B is the natural log of the starting concentration, so you need to actually take the exponential of B to get the starting concentration. And for second order, y is 1 over the concentration. So B is 1 over the starting concentration. So we need to take 1 over B in order to find that starting concentration. But let me just check on my end to see if it's just an issue of significant figures. On Blackboard, you can do it. Yeah, so for 1, you need to take the exponential of that y-intercept. And for 2, again, you need to take the exponential for that one. 3, because it's natural log, you'll take the exponential. So yeah, that's more the issue, is that you are correct, it's related to the y-intercept, but isn't necessarily equal to the y-intercept. It depends on if you're looking at a 0 first or second order plot. So it's really just the form of the equation. So you're not being asked, so look at 0 first and second. You got A, So for zero order, if we want to know what the starting concentration, so for all these, the starting concentration is when time equals 0. So that term disappears from our equation. And in all of our graphs, we would just ignore the mx part, and we would just get y equals b. The problem here is the form of y. So for first order, y is the natural log of the concentration. So at time equals 0, we're not looking at starting concentration, we're looking at the natural log of the starting concentration. So in this case, it's the natural log of the starting concentration that equals the y-intercept. And for this one, we get that y is 1 over the starting concentration. So that's equal to b. So because you're graphing natural log of a, that's what the starting concentration is going to be if you take time equals 0 on that particular graph, because that's what you're plotting. Just because you're at time 0 doesn't mean it equals the starting concentration. It equals whatever y is. I don't know if that helped you or not. I love like this 1 minute lag. So if you have any graph, f of x equals, let's say it happens to be some mx plus b. Actually, no, that's probably not the best way to explain it to you. So let's just look at the zero order case. So what we're looking for is the starting concentration, and we're going to take this at time equals 0. So time equals 0 is this point here, and it's wherever it intercepts here. But the thing is that we're not plotting concentration versus time, we're plotting the natural log of concentration versus time. So just because you're at time 0, you're looking at a point where the starting concentration is 0, but that's the y-intercept. We're not looking at concentration. What we're looking at is the natural log of concentration. So this point here is a function of the starting concentration because we're at time equals 0, but it is not necessarily the starting concentration. Whereas if you look at concentration versus time, when we have time equals 0, we have whatever y is at time equals 0, and in this case, our y is equal to the concentration. Oops, wrong way. If you look at 1 over concentration versus time, so we got our y-intercept there, time equals 0. This is going to be related to the concentration at time equals 0, but because y here is 1 over starting concentration, it's not going to be equal to the concentration. So you can't have this statement. And you can't have this statement here. Like, both those statements are false. So it's more just a nature of the plots. Whenever you go to time equals 0, your form of y has to be whatever this y-axis is. In this case, for first order, wow, that's illegible first. That's natural log, and for second order, it's 1 over concentration. Now, the easiest way probably to see this, and I can bring it up on my end for you to see it, is how we actually construct the plots in the first place. Oops, sorry, wrong one, desktop. So if we want to figure out data set 5 was first or second order or 0 order, we look at natural log and 1 over concentration. So let me just do that calculation really quick. And building to a point, okay. So let's say I create my 3 plots, concentration versus time. Natural log of concentration versus time. And 1 over concentration versus time. So from this data, we know what the starting concentration is because at time equals 0, it's 0.25 molar. And, oh, that's really annoying. So we know whatever the starting concentration is, whatever these graphs produce, in order to backtrack out what the starting concentration is, we need to get 0.25. So if I look at concentration of A versus time, I get that roughly 0.25 here. It's 0.2458. That's just because there's noise built into this data. So we can see here the y-intercept does numerically equal 0.25. If you look at ln of A versus time, the y-intercept here is actually minus 1.4029. So we know this isn't true because the starting concentration is 0.25. So the y-intercept here doesn't equal the starting concentration because it's not the starting concentration, it's actually the natural log of the concentration. So in order to undo that, we just take the exponential, and you see when we take the exponential of the y-intercept, we get the 0.245883, which is a lot closer to that 0.25. For the 1 over concentration versus time, our y-intercept here is 4.0227. Again, we know the starting concentration is 0.25. We have that in the data. So here the y-intercept can't possibly be the starting concentration because we know it's 0.25. But if we do 1 over that number, we get the 0.24589, again close to that 0.25. So it's the nature of the graph. We are plotting 1 over concentration versus time, so if we look at time equals 0, we're not looking at starting concentration on these plots. We're looking at 1 over the starting concentration because that's what we had to do here in order to generate the plot. Same thing's true of the first order. The first order, the y-intercept isn't concentration, it's natural log of concentration because that's what we had to do in order to produce this plot. So if you think about it in terms of math, we will always get an equation y equals mx plus b on our graph. And the starting concentration is going to relate to when x equals 0. So when x equals 0, for 0, first, and second, the thing to keep in mind is that in order to create our plots, for 0 order, we literally just plot concentration versus time. So y here, as a function of starting concentration, is just starting concentration. For first order, y is the natural log of the starting concentration. For second order, it's 1 over. Because y here is not starting concentration, it's a function of concentration. So in order to generate each of these plots, we had a different function for what the y is. Yeah, you're welcome. It's kind of the first time you've really had to deal with this, though. And so, like, instructors, like, we definitely see this a lot, particularly when we start getting to this test 2 material, is that and you know, we can kind of knock math education for this. Like, you're not used to having to, like, do this. Like, usually y is whatever you're searching for. In this case, y is actually a function of concentration. So you just have to keep in mind what that function is. So if I have first order graph and we were solving for k, would you take the natural log of a? So actually, this is why we do the graphical analysis. So in principle, you can do that. So let's say you had ln of a versus time. And it ended up being a straight line. I'm going to try to draw this so it's easy to see the point I'm trying to make. And in principle, you can look at the slope between points, but the thing is that each point has its own slope. Or every 2 points have their own slopes. So you can see here how some slopes are higher than others or lower than others. So the question is, what do we take? And the answer is we take the linear regression. Because your eye can probably see that there's kind of an average slope, and that's your y equals mx plus b fit. So the reason why we want to go across all lines is that the slope here is an average of all slopes. So all 2-point slopes. So this will average out any uncertainties between data points. Again, you can go through and you can do 2 points. Generally speaking, though, this is why we just measure concentration versus time until the reaction dies. Because the more points we take, the more we're going to start averaging and the more accuracy we get. So if we have n data points, I think your accuracy goes as like the square root of n. So the more and more points you're averaging here, the more and more accurate your answer is going to get. But yeah, you would just use the slope from the linear regression. You wouldn't bother trying to take the individual slopes because they're all going to have errors embedded into them. The slope that you get from fitting all the data, that's going to average out all those errors. And this is an issue with method of initial rates. So with method of initial rates, let's say for whatever reason you could hypothetically generate a super high precision reaction. So let's say we have time equals 0, and here we have time, but it's a very small increment of time. We would still get different slopes. And particularly as the reaction runs along for method of initial rates, the slopes get smaller and smaller because the reaction begins to slow down. And for method of initial rates, you're averaging across whatever this time gap is, that's going to introduce errors. Basically, it's going to Yes, so for 0, first, and second order, it's just the M value. That's your rate constant, K. But yeah, for method of initial rates, there's a better way to illustrate this. So method of initial rates, we've got rate versus time. And let's say this is the theoretical, or yeah, this is the theoretical rate. So the actual slope is going to look like this. But we're not measuring there. We're having to measure finite time points. So let's say we go here. Well, if we measure between this point and this point, we measured a lower slope. And let's say we measure here. If we measure here, that's the rate we measure. And as we start getting progressively further and further out in our time measurements, the rate begins to slow down because the reaction slows down. So for method of initial rates, this is a major issue, because as I start pulling closer and closer to the starting concentrations or the starting rate, I'm going to get a more and more accurate number, but this isn't necessarily feasible to do. Yeah, average of slopes, you're probably going to get closer and closer. You probably found that you're getting closer and closer to that M value. So, yes and no. The short answer is yes. A rate law can have intermediates, but we practically don't want them in there. So you had the discussion board question, CH3, CH2, Br goes to CH3, CH2 plus Br minus, H2O goes back and forth to H plus and OH minus, and then CH3, CH2 plus OH minus goes to, I'm going to write reversibility errors here for a reason, goes to the alcohol. So in principle, if you want to write let's say this was the rate limiting step. So the rate of the reaction here is K concentration of CH3, CH2 plus, and OH minus. This is not an incorrect statement. You can definitely write this. The problem is that we don't have either of these. So if we want to figure out the rate of reaction, we would prefer to start on things like these two, because we can add these to the reaction. Now let's say if these reactions are reversible, well, we know we got Kw equals concentration of H plus OH minus all over concentration of H2O. Actually, that's unfair. We know we can measure hydroxide concentration directly. But for the first reaction, we've got CH3, CH plus, Br minus, all over concentration of CH3, CH2, Br. We could rearrange this equilibrium expression to plug into this, and that would give us hydroxide, bromide, and our starting reagent in the equation. And that would be a lot more useful because we can control bromide concentration by adding something like sodium bromide. This we can add directly, and this we can add something like sodium hydroxide. So short answer is yes, you can have intermediates in there. There's nothing wrong with it. Practically, you don't want intermediates because you can't control their concentrations. So the stream's actually going, oh, I can type it for you. So yeah, it's fine to have intermediates, it's just not practical. And this would be something you cover in a higher level kinetics course, is how you would take the intermediates and start getting rid of them. There are two approaches to this. One is the pseudo steady state hypothesis, and there's another where you assume all the reactions are at equilibrium prior to the rate limiting step. It's not hard, it's just a lot of algebra. It's kind of outside the scope of this course. But yeah, you can definitely have them in there, just you can't control the concentration of intermediates, so they're not really that useful. All right, so we've come up to 11 o'clock. I need to head out, but thanks, Dia, for showing up. A lot of good questions, actually. And always with the live stream, yeah, you're welcome. As with the live streams, always feel free to ask questions in advance. And I will see some of y'all tomorrow.